Hello, statics class. This is your instructor, Laura Worth, and I am recording some equilibrium analysis examples for you to help you with your study for Exam 2. Today is February the 12th, and Skagit Valley Community College is closed. This is our second lecture day we've missed due to weather, and so I'm trying to give you a little bit of screencast assistance to your studies of equilibrium analysis. So these are more examples that I would have used in live lecture, and so this is our virtual exercise together, hopefully. So we're starting out with a given. This is a cable problem, and this is a cable such as you would see used for maybe stringing signal lights for traffic. So we have over here on the left-hand side maybe a wall or a pole or something, and you have a fixed point, and then the cable is strung to a point where you have a 50-pound weight that is clamped to it. So there's friction definitely between that 50-pound weight that's being exerted obviously in the downward direction, and then a length of cable between. You have another weight clipped, fixed to the cable at that spot, and then the remaining length of the cable is fixed to another, like say a wall or a pole. And so our geometry here is practically straight. We have 22 feet between the wall and the first weight, 22 feet between the two weights, and then 22 feet between the weight and the far wall. And the sag, the extent to which the cable has deflected, is only 8 inches, or 2/3 of a foot. And so the question is to find the tension in the cable. So obviously it's going to be a lot more than it would be if it was straight and if there were no weights on it. And so what we're going to do is we're going to do a free body diagram of different points in that cable to solve for the cable tension. And so this is really our first encounter, even though we haven't introduced friction per se yet. This is almost an extreme example of friction because we're not allowing that weight to slide on the cable at all. We're clamping it firmly in place. And so this is our first instance where we don't have a frictionless cable. So the tension on one side of that weight and the tension on the other is going to be completely different. So we're going to start with our geometry here. So we're going to start by getting the angle, since we're going to set up to do some of the forces in the x and the y, of course, get those equal because that's pretty much our only way of doing the analysis. So we're going to need that angle to start resolving the tension in the cable on those two flanking sides. So we just used the tangent of that angle being 2/3 of a foot over 22 feet. So a tan of 2/3 over 22 ends up being 1.7357 degrees, not very much. So we're not going to expect a lot of difference in the tension on that angled cable and its cosine. And in fact there isn't, but there is a little bit. So here's the meat of it, right down here. We've got one of these weights isolated, and in fact this is the left-hand weight. So we have, if we do a free body diagram around the point at which the weight is clamped on the cable, so if we imagine that weight, just being clamped with a clip, it's kind of like we're doing a free body diagram of the clip. So we have 50 pounds in the negative J direction, the downward direction. We have tension 2, which is the tension between the two weights. So we basically sawed the cable in half and represented its resultant force with just some tension. We'll call it T2 because we don't know what it is. And then we did the same thing with the cable going to the left-hand wall, and we're calling it T1. Now we know its direction. So we know it's pointing in an angle of theta, which is 1.7357 degrees, upward and to the left. So easy. Let's see, I have two unknowns, T1 and T2. I have two equations available to me. I don't have a moment equation because all of the forces are concurrent. They're all going through the same point, so they can't exert a moment. So all I have are the sum of the forces in the x and the sum of the forces in the y. I have two equations, but I only have two unknowns, so I'm good. And here are my equations. Here are the equations of equilibrium. The sum of the forces in the x is going to be the cosine of T1 minus T2 equals 0, or I can write it this way. That puts them equivalent. So the T2 equals T1 cosine theta. there is the sum of the forces in the X, and then if I write those same equations of equilibrium, I have T1 times sine theta equals 50 pounds. So solve for both. I know theta, and I get T1 equaling 1,651 pounds, and T2 equaling 1,650 pounds. So that's quite a bit. Let's check to make sure that's reasonable and written correctly. Tension in the outer sections is 1 pound more than in the inner sections, and it's quite a lot. So basically we're asking something to work off angle. We're only holding up 50 pounds, but because we're forcing ourselves to only have a very small component of the resultant force to do it in, we're ending up needing a tremendous cable tension to do that with. So that ends up being the solution, almost 1,600 pounds, 1,650 between and 1,651 on the outer, just to hold up two 50-pound weights. So definitely need a strong cable to do that. And that is it for this example, and we'll come back with another example.